Next up, we have number 3 of the top 10, high-performance walls. At the good level, we'll look at intermediate or advanced framing with blown-in insulation. At the better level, single plate with staggered stud and blown-in insulation, or a 2x6 with exterior continuous insulation. And then at the best, double stud with blown-in insulation, or again 2x6 with exterior continuous insulation. By switching to blown-in insulation with a standard intermediate frame 2x6 wall, you have upgraded the wall to the good level of high performance. The blown-in insulation not only provides a higher level of R23 compared to the standard R21, it also gives a much higher quality install and consequently a higher overall performance compared to a standard install of fiberglass batts, as we looked at earlier. To take the R levels higher and move to the better category, you need to make the wall thicker. And two options for taking the wall up to as high as R27 are to build a staggered stud 2x4 wall on a 2x8 plate, or adding exterior continuous insulation to a standard 2x6 wall. In both cases, you not only increase the insulation level, but now you have significantly reduced the thermal bridging across the wall through the studs. In the staggered stud wall, the studs do not create a conductor from inside to outside, so this cuts off that bridge for heat to transfer. With the 2x6 wall plus continuous insulation, that exterior insulation restricts heat loss through the studs because the continuous insulation protects the edge of the stud and sheathing from the exterior temperatures. Here we can see photos of a staggered stud wall and the infrared shot of the same wall showing its temperatures. The studs are visible and slightly cooler than the surrounding insulation, but they're not transferring that heat to the outdoors because, of course, they don't span across the wall cavity. We can see the bottom plate is still acting as a thermal bridge in this wall because it does span across the assembly from inside to outside. But the thermal bridging overall is way less in this wall than in a standard 2x6 wall. We can also see there is some air leakage happening under the bottom plate because unfortunately it was not air sealed with a seal sealer or similar, and this is represented by the dark blue color. Here's a closer look at the configuration of the studs in the staggered stud wall. It's usually built with 2x4s, 12-inch on center, which then results in 24-inch on center for each side of the wall. It can provide an R25 insulated assembly with blown-in insulation installed. Another better wall option is to build the 2x6 wall and then add 1/2 to 3/4 inch continuous insulation to the outside, and you could get up to an R27 if you're using blown insulation inside the wall. There are many different types of exterior insulation to choose from, and here are some of the most common. XPS, which is extruded polystyrene, EPS, expanded polystyrene, polyisocyanurate, mineral wool panels, and other less common options include expanded cork, rigid fiberglass, cellular glass, low-density wood fiber, and perlite board. When you add continuous insulation to the outside of your wall, your crews installing the weather-resistive barrier and window flashings have to integrate this extra layer of insulation into these systems in order to manage the exterior water, and this can require some extra planning and training to make sure it's done correctly. But another option for adding continuous insulation is to consider using what is known as the thermal break shear wall, or TBS. And this is installing the continuous insulation between the studs and the sheathing. And the advantage of this method is that your flashing and WRB is installed with standard techniques and details over the sheathing. When you choose the exterior insulation, don't forget that it can affect the wall's drying potential to the outside. In this chart, we can see the common insulation types vary quite a bit in their permeability depending on the type or thickness. It's less risky in the long run to avoid using exterior insulation that is impermeable so that the wall can dry. For example, if you wish to take advantage of the high R value per inch that polyisocyanurate offers, it's best to choose the fiberglass-faced polyiso version because the foil-faced version is vapor impermeable, but the fiberglass-faced type is vapor semi-permeable. Here are photos of a wall built with exterior foam insulation. The field portion of the wall is quite even in temperature in the IR photo, demonstrating good performance. But these dark areas are again air leakage at the edges and transitions, And this shows that you need to take a comprehensive approach to high performance by not only adding more insulation, but also air sealing to protect the insulation for optimum performance of the entire building shell. Here are photos of a wall built with exterior foam insulation. The field portion of the wall is quite even in temperature in the IR photo, demonstrating good performance. But these dark areas are again air leakage at the edges and transitions, and this shows that you need to take a comprehensive approach to high performance by not only adding more insulation, but also air sealing to protect the insulation for optimum performance of the entire building shell. There are a number of special fasteners available for attaching continuous exterior insulation. We also see long, specially designed screws on the right, which are for attaching battens over foam when you want to build a ventilated rain screen, and then the battens can hold the foam in place. Another way to get to a higher R value wall is to use spray foam. Spray foam's high R values per inch can quickly create a high performance wall with high resistance to heat flow and excellent air sealing. Unfortunately, this also usually comes at a much higher price point. Some builders like to use spray foam combined with fiberglass bats to get to a higher R value and air sealing at a lower cost than that of filling the wall with foam. This is commonly called flash and bat. A thin layer of spray foam goes in against the sheathing, followed by a fiberglass bat to make up the remainder. Although this makes for a higher R value and great air sealing, it does not eliminate the thermal bridging of the studs, so the overall wall performance still takes a hit from that conductive heat loss. This is also true for walls filled with spray foam. Conductive heat loss will happen through those studs, but simply adding continuous insulation to the outside will shut down that thermal bridging, add R value to the wall, and is considerably less expensive to the spray foam option. Now let's look at the walls in the best category, where you can take the wall insulation above R27. Again, to get there, it simply takes a thicker wall. You can build this with a double stud wall, or you can add even more continuous insulation to the outside of a 2x6 wall. By adding 1 and up to 4 inches of continuous insulation to the outside of a 2x6 wall, you can achieve an R value of R27 up to R43, depending on the type of insulation you choose. Of course, the thicker the continuous insulation you use, the trickier your flashing details become at the window and door penetrations. The flashing materials must integrate with the weather-resistive barrier for effective bulk water management. A couple of good resources to look at for these flashing details are at the Building America Solution Center in the Continuous Rigid Insulation Sheathing and Siding section, and the Construction Guide, Next Generation High Performance Walls, published by Building America and Home Innovation Research Labs. We'll make these online links available to you in the resources page of the course for easy access. For the double stud wall option, you can go to higher and higher R values by simply increasing the overall width of the wall. R28 to R50 is possible, but you want to be careful not to go beyond the point of diminishing returns and build the appropriate R value to your climate zone. And this is where using energy modeling can really help dial in the R value needed to reach the overall energy performance goals of your project. The double walls need to be capped off and tied together across the top plates with OSB or plywood to make a continuous air barrier. Window bucks made of OSB or plywood are installed to tie the walls together and create a rough opening that can be properly air sealed. Here we see an example of a double stud wall constructed with two 2x4 walls spaced approximately 4 inches apart. For 2-story houses, the exterior wall would be constructed with a 2x6 for structural support of the second floor. As you can see, the rough-in work for the electricians and plumbers can be substantially less labor-intensive since wiring and supply pipes can run through the gap between the walls, eliminating the need for much of the drilling that's typically involved. For the insulator, installing blown-in product, it will involve a change of workflow. They either need to fill the wall cavity in a series of lifts, building it up towards the top to achieve the required density because the whole wall cavity is connected, or they may install netting between the studs to create bays that they can fill up as they normally do to get the density of insulation needed. Section 4 is high R value ceilings. At the good level, we're looking at a standard truss with an R21 high-density fiberglass bat or rigid insulation insert. Better is moving to a raised heel truss or parallel cord cantilever truss. At the best level, true vaulted ceiling or insulated roof above attic. Even when you have your attic insulated to R49, it may not be achieving that performance due to the geometry of the standard truss with low-pitched roofs. Where the truss meets the top of the wall, we have a pinched area with less than a full depth of insulation, which compromises the overall R value of the attic. So you might be thinking, okay, but how big of an impact can this really have? Well, let's do another weighted R value calculation to see how an attic performs across the entire area, just like we did in Module 1 with that example of an uninsulated attic hatch. So let's take a 1,200 square foot attic insulated to R49, and it's a 30 foot by 40 foot shape, and let's say 1.5 feet of the pinched eaves along the 40 foot length as a lower amount of insulation. So the pinched area across the entire house would be 80 feet long times 1.5 feet for a total of 120 square feet at an average of R24. So we'll subtract that area from the 1,200 square feet, and that leaves 1,080 feet insulated to R49. If we do a weighted area calculation on the entire assembly, the R49 will actually only achieve an R44, which is pretty significant at a 10% degradation. At the minimum, you want to increase the insulation where the pinch is the tightest, which is right at the top of the wall. So taking this to at least an R21 to match the insulation inside the wall will take you to the good level. You can increase the insulation R value above the wall top plate with a high density fiberglass bat or by adding a block of rigid foam insulation. To take this assembly to the better level and get a full depth of R49 across the whole attic and across the top of the wall, the easiest solution is to use a raised heel truss. The truss is constructed so there's enough height to blow the full depth of insulation all the way to the edge of the attic and over the top of the wall, with enough space for the ventilation baffle as well. Using tall parallel cord or scissor trusses with the necessary height to get a full depth of insulation work well and move up to the best category. Another method is to use I-joists to move the thermal boundary to the rafter line. The best level idea here is that by moving the thermal boundary and insulation layer up to the rafter level, you can use this volume that you're building anyway for useful space and a value add to your customers. If the roof pitch allows, of course, you can add more living space. But even when the design calls for a flat ceiling, you can still use one of these methods to create a conditioned attic. After all, who doesn't need more storage area? And this becomes a great space to use for bringing the ducts and HVAC inside the conditioned space, which we'll cover more in Section 6. Number 5 of our top 10, windows. At the good level, we'll choose proper U value and solar heat gain coefficient for different applications. Better, we'll focus more on window design to avoid too much glazing. And at the best level, add daylighting and high-performance low U value windows. Window energy efficiency ratings are expressed in U value instead of the R value like we use for insulation. The joke is that they use U values because they want to disguise the fact that the windows are really bad compared to insulated walls. For example, a 0.30 window has an overall R value of only 3.3. But the real reason the U values are used is because it is rating the entire window assembly, the glass, spacers, and frame, and not just one material. Since heat loss is strongly affected by the amount of surface area, walls of glass in a house will greatly lower the overall performance of the shell. So smart placement of appropriately sized windows is a key strategy to address when designing for high performance. So with windows, the heat loss is expressed by the U value, the heat gain by the SHGC, which stands for solar heat gain coefficient. The amount of light that comes through the windows is the VLT, or visible light transmittance. The SHGC and the VLT are related, as we see in the graphic. With a low SHGC window to block excessive heat gain from the sun, it will also let less light through the window. A good window with a U factor of 0.25 translates into an R value of R4. And if you compare this to the R23 walls surrounding the window, It's losing heat about 6 times faster than the insulated portions of the wall. So this is why you want to try to keep your window to floor area ratio below 21% to reduce heat loss in the winter and keep heat out in the summer. At the good level, aim for U value of 0.25 or lower. Essentially, you want to buy the lowest U value your budget will allow, as we are in a heating-dominated climate zone, which means the majority of our conditioning energy is used in the wintertime for heating, so limiting heat loss is our primary goal. When possible, you want to customize the SHGC by orientation. On the east and west sides of the building, it's best to go with a low SHGC, which will keep summer heat out when the sun is at a low angle in the morning and evening. But on the south side, you want to use a higher SHGC in order to accept heat in the wintertime, and this is a tempered solar design strategy. You can protect those south-facing windows in the summer from heat gain with larger overhangs or other shading strategies. To move to the better level, optimize your window in addition to using the U.25 windows or better at the good level. You optimize by orienting the building and placing most of the windows on the south-facing side whenever possible, and then limit windows on the east and west to avoid excessive heat gain. Choose fixed windows wherever appropriate because they generally have a lower U value. And then strategically frame views with larger picture windows to highlight the view toward the living space, instead of installing glass walls floor to ceiling where the view essentially becomes wallpaper and the heat flies out of the building. Allow for cross ventilation with operable windows smartly placed that will passively air out the home when the weather is nice. To go to the best level, install windows with U values at 0.20 all the way down to 0.09. These are usually triple pane low E windows with an argon gas fill and a double air sealing gasket built into the frame. There is a new exciting option for triple pane windows that is starting to come to market. Often referred to as thin triples, these windows have a very thin piece of glass for the middle pane, significantly lowering the added weight of the unit. Thin triples are lowering the cost of high-performance windows because the reduction in weight allows manufacturers to use a lower cost frame component compared to traditional triple pane windows that require a substantial increase in frame structure. Ask your window supplier about thin triple pane windows. So again, design the largest area of windows facing to the south. To optimize those south-facing windows, we want to shoot for a solar heat gain coefficient of greater than 0.6 to maximize the solar heat gain during the winter, and a U factor of 0.2 or less to reduce conductive heat transfer. Rooms that are the most occupied and have the greatest heating and lighting requirement should also be built along the south face of the building. North-facing windows collect very little solar heat, so they're used really only for lighting. You should design the smallest area of windows facing to the north when possible. Other design strategies would be to have rooms that are the least used, like closets, storage areas, or even garages, placed along the north wall where they can act as a buffer between the high-use living space and the cold north side. Daylighting design strategies are to use light-colored interior finishes to help reflect light, and then share light between spaces with things like internal windows, high-end partition walls that allow natural daylight to penetrate further into the building. Another effective, energy-efficient strategy for daylighting is to use tubular daylight devices. They're a great way to bring light to a space while minimizing glazing area and heat loss. It's key to install tubular daylight devices with a double pane lens at the ceiling rated with a low U value and an air seal at the ceiling penetration. You also want to insulate the shaft. These can be an excellent alternative to skylights, which have a larger area for heat loss and gain, not to mention the challenges of air sealing and insulating the skylight shaft that we covered earlier in the air sealing section. Number 5 of our top 10, windows. At the good level, we'll choose proper U value and solar heat gain coefficient for different applications. Better, we'll focus more on window design to avoid too much glazing. And at the best level, add daylighting and high-performance low U value windows. Window energy efficiency ratings are expressed in U value instead of the R value like we use for insulation. The joke is that they use U values because they want to disguise the fact that the windows are really bad compared to insulated walls. For example, a 0.30 window has an overall R value of only 3.3. But the real reason the U values are used is because it is rating the entire window assembly, the glass, spacers, and frame, and not just one material. Since heat loss is strongly affected by the amount of surface area, walls of glass in a house will greatly lower the overall performance of the shell. So smart placement of appropriately sized windows is a key strategy to address when designing for high performance. So with windows, the heat loss is expressed by the U value, the heat gain by the SHGC, which stands for solar heat gain coefficient. The amount of light that comes through the windows is the VLT, or visible light transmittance. The SHGC and the VLT are related, as we see in the graphic. With a low SHGC window to block excessive heat gain from the sun, it will also let less light through the window. A good window with a U factor of 0.25 translates into an R value of R4. And if you compare this to the R23 walls surrounding the window, it's losing heat about 6 times faster than the insulated portions of the wall. So this is why you want to try to keep your window to floor area ratio below 21% to reduce heat loss in the winter and keep heat out in the summer. At the good level, aim for U value of 0.25 or lower. Essentially, you want to buy the lowest U value your budget will allow, as we are in a heating-dominated climate zone, which means the majority of our conditioning energy is used in the wintertime for heating, so limiting heat loss is our primary goal. When possible, you want to customize the SHGC by orientation. On the east and west sides of the building, it's best to go with a low SHGC, which will keep summer heat out when the sun is at a low angle in the morning and evening. But on the south side, you want to use a higher SHGC in order to accept heat in the wintertime, and this is a tempered solar design strategy. You can protect those south-facing windows in the summer from heat gain with larger overhangs or other shading strategies. To move to the better level, optimize your window in addition to using the U.25 windows or better at the good level. You optimize by orienting the building and placing most of the windows on the south-facing side whenever possible, and then limit windows on the east and west to avoid excessive heat gain. Choose fixed windows wherever appropriate because they generally have a lower U value. And then strategically frame views with larger picture windows to highlight the view toward the living space, instead of installing glass walls floor to ceiling where the view essentially becomes wallpaper and the heat flies out of the building. Allow for cross ventilation with operable windows smartly placed that will passively air out the home when the weather is nice. To go to the best level, install windows with U values at 0.20 all the way down to 0.09. These are usually triple pane low E windows with an argon gas fill and a double air sealing gasket built into the frame. So again, design the largest area of windows facing to the south. To optimize those south-facing windows, we want to shoot for a solar heat gain coefficient of greater than 0.6 to maximize the solar heat gain during the winter, and a U factor of 0.2 or less to reduce conductive heat transfer. Rooms that are the most occupied and have the greatest heating and lighting requirement should also be built along the south face of the building. North-facing windows collect very little solar heat, so they're used really only for lighting. You should design the smallest area of windows facing to the north when possible. Other design strategies would be to have rooms that are the least used, like closets, storage areas, or even garages, placed along the north wall where they can act as a buffer between the high-use living space and the cold north side. Daylighting design strategies are to use light-colored interior finishes to help reflect light, and then share light between spaces with things like internal windows high in partition walls that allow natural daylight to penetrate further into the building. Another effective, energy-efficient strategy for daylighting is to use tubular daylight devices. They're a great way to bring light to a space while minimizing glazing area and heat loss. It's key to install tubular daylight devices with a double pane lens at the ceiling rated with a low U value and an air seal at the ceiling penetration. You also want to insulate the shaft. These can be an excellent alternative to skylights, which have a larger area for heat loss and gain, not to mention the challenges of air sealing and insulating the skylight shaft that we covered earlier in the air sealing section. Number 6, ducts and distribution. At the good level, we'll seal the ductwork with mastic paste. At better, seal the ducts with mastic and test the ductwork for air tightness. And at the best level, bring the ductwork inside the conditioned envelope or go with a ductless HVAC system. The problems with ducts can contribute to a long list of negative effects on the home's energy performance. Inadequate levels of insulation lead to heat gain and heat loss. Too much duct air leakage is another direct loss of energy, and the duct leakage can also introduce pressure differences in the building envelope, leading to further air leakage to happen and more energy loss. Consequently, ducts can be responsible for up to 20% of building heat loss. So sealing the ducts with a robust and long-lasting material is the ticket. The good level is to seal the ducts with mastic paste. It should go on all the joints, seams, rotating joints, etc. Basically anywhere the pressurized forced air can leak out. The mastic needs to be spread on as thick as a nickel for a full-strength seal that will last the lifetime of the distribution system. To take it to the better level, have the sealed ductwork tested for air leakage to ensure no places were missed with the mastic paste. This is another quality control check that your project and customers will benefit from when you work with a third-party verifier. In the majority of new construction today, the HVAC is located in the attic. And this is generally a bad idea because the equipment and ducts are now located in an outdoor environment, very cold in the winter, and even worse in the summertime because attic temperatures can often exceed the outdoor temperature. This leads to an increase in the total heat loss and heat gain. And then the ducts, if they are leaking, cause air exchange between the house and the attic. And heating the attic can lead to ice dams. And it makes it difficult to access and service the equipment, unless you bring the ducts inside the conditioned envelope. And one way to do that is to bring the attic inside the conditioned space. There's a number of other ways to bring the ducts inside that we'll look at next. Bringing the ducts inside takes us to the best level, as this is one of the best ways to improve overall building performance. It can also reduce the cost of the HVAC system. It can reduce the length of the duct runs, and it can eliminate the need to insulate the ducts. So why do we want to bring the ducts inside? Because it makes sense to put them in a conditioned environment. As we know, heat transfer increases when the difference in temperature is larger. You also safeguard against condensation that can happen in the summer if there's humid outdoor air that can condense on the cold ductwork because cold air is flowing through the ducts from the air conditioning. And if any leaks do develop in the ducts in the future, there's no negative effects because now they're located inside. There's no pressure drive and no energy loss to the outside. So how do we go about doing it? Well, it's most cost-effectively done when you start with the design, well before construction begins. And there's a number of ways to put the ducts inside, including running them through drop ceilings, soffits, interior walls, unvented crawl spaces, and conditioned attics. So you either move the ducts and air handler to conditioned space, and/or turn unconditioned space into conditioned space where the equipment and ducts are already located. For a two-story home, you can place the air handler in a closet and run the ducts in the cavity between the top and bottom floor. If you're building a home that has a conditioned basement, you can put the air handler in the basement and then again run the ducts through the floor joists. Drop soffits can provide a space for duct runs. This is often done in homes with 9-foot ceilings, and then the hallway ceiling is dropped to 8 foot to create a space for the ductwork. Open web floor joists are a great option to provide the space for the ducts to run through the ceiling floor assembly. Another approach that has been used is to order trusses that are framed so that you can run the thermal boundary up and around a plenum space for the duct runs and still end up with an uninterrupted flat ceiling. Or as we mentioned earlier, in the high-performance ceiling attic section, you can create a conditioned attic by moving the thermal boundary to the rafters and then place the air handler and ducts in this thermally protected and air-sealed attic, with the added bonus of providing climate-controlled storage space. Another approach to ducts inside is to bring the crawl space into the conditioned envelope and place the HVAC and ducts below the ground floor. So if you're thinking about making the switch to ducts inside, the best approach is to research the different options to see what could work best with your designs. A great place to start is to visit the website ductsinside.org. You can consult with your verifier for advice. You want to bring both the designer and the HVAC contractor into your planning early to figure out what will be the most cost-effective solution. Start slowly and adapt your designs over time. And then finally, be persistent. Although this is a challenging change, it can reap big rewards for getting your projects to the higher levels of energy performance. Another way you can get to the best level for HVAC distribution is to simply eliminate your ducts altogether and go with a ductless system. Ductless heat pumps for heating and air conditioning is an option, or perhaps hydronic heating if your location does not require air conditioning. Going duct-free eliminates all of the potential problems with heat gains and losses, duct leakage, and the pressure imbalances caused by the leaks. Number 7, fresh air ventilation. As we discussed in the air sealing section, people need fresh, high-quality air in their homes, so all high-performance homes need to have a whole house ventilation system to essentially be the lungs of the house. At the good level, we'll be looking at exhaust-only ventilation systems. To take it to better, supply ventilation or supply plus exhaust ventilation with an ECM blower motor. And at the best level, heat recovery ventilator or energy recovery ventilator. Ventilation systems provide many functions. They remove odors and pollutants like chemicals in the form of volatile organic compounds or VOCs, and they remove water vapor that is constantly being created by the daily activities of the homeowner. As the bad air is removed from the home, it needs to be replaced with fresh, clean air in order to keep the indoor air quality high so that we can live in a healthy home. So at the good level, you install an exhaust-only ventilation system. This consists of an upgraded bath or laundry room fan that's Energy Star rated and is quiet with a low SON rating. Then the electrician wires this fan to a programmable 24-hour 7-day timer so that it can be automated. The timer is programmed to turn the fan on for the prescribed length of time to meet the ventilation needs of the home, and this is based upon the size and number of bedrooms in the home. This is the most basic of systems. To move to the better level, you can install a supply ventilation system. This brings air into the return side of the HVAC air handler to use the ductwork for distribution. It'll have a motorized damper to close the fresh air duct when the system is off. A key detail is to make sure the HVAC air handler fan has an energy-efficient electrically commutated motor or ECM motor, because older style single-stage motors use a lot of energy and is not an efficient way to ventilate the home. Supply systems also have a timer controller to program just the right amount of air for the size of the home. The controller will open the damper when the HVAC comes on and keep track of how long it runs. If the house needs more ventilation air than what came in during the heating and cooling cycle, it'll kick on the air handler fan and open the damper to deliver more fresh air. The downside of this system is that it slightly pressurizes the house because it's not a balanced system. But this is pretty simple to overcome. To balance out a supply ventilation system, you can simply have the electrician tie the controller to a quiet bath fan so that the supply air coming into the ducts is balanced out by the stale air that's exhausting through the bath fan. At the best level, you install an HRV or ERV, which stands for Heat Recovery Ventilator or Energy Recovery Ventilator. These are designed as balanced systems with both supply and exhaust ducts. They can have independent ducts for distribution, or they may be tied in to use the HVAC ducts. These systems provide the best mixing of air to evenly deliver fresh air throughout the home. The other big advantage of these systems is that they have heat exchangers built in that will recover heat energy. In the wintertime, the warm, stale air will transfer its heat to the cool, incoming fresh air. This saves energy and increases comfort. There are also smaller versions known as spot ERVs that are useful for smaller areas, because they provide ventilation, both supply and exhaust, at the ceiling grill without distribution ducts, which can make it a more economical way to add heat recovery ventilation to a small home. The ventilation air from a spot ERV will not be as well distributed throughout a home without help from some other systems such as transfer fans or a ducted forced air system. Another innovative ventilation system is a through-the-wall ERV. This has a heat exchanger and a fan built into the wall through a short direct duct passing from indoors to outdoors. It works with a second unit in tandem on the other side of the building. One will run supply air for just over a minute while its companion fan pulls exhaust air out. Then they switch roles and reverse the airflow. As the air flows through the ceramic heat exchanger, the heat is captured in the core of the fan that's working as the exhaust fan, and then the heat is released into the fresh air stream when that fan becomes the supply fan. It takes advantage of the basic principle of heat moves from warm to cold. So when choosing the right ventilation system for your project, you'll want to think about these considerations: efficiency of motors and efficiency of heat recovery if you're going with a HRV or ERV. For low operational energy, always use ECM motors. The airflow rating of the system must be able to meet the needs of the home based upon its size. Freeze protection is key for ERVs and HRVs. They must be located in a buffered or conditioned space. Noise is a consideration. You want to make sure your system is quiet, otherwise the homeowners will just turn them off. Variable speed is an option for some systems that can give more flexibility in meeting the ventilation requirements. Unit dimensions for designing the necessary space for installation. And then maintenance requirements. The homeowner has to be able to easily access the units for cleaning and filter replacement. Other options available with ERVs and HRVs can be filtration, advanced controls, and self-balancing, which can be helpful to minimize pressure imbalances in the home. Number 8, lighting and appliances. At the good level, we want to choose Energy Star appliances and lighting. At the better level, add a heat pump clothes dryer. And then at the best level, add an induction cooktop. Choosing energy-efficient lights and appliances is relatively easy because of the Energy Star rating. Manufacturers have embraced the program, and there are scores of energy-efficient options available for refrigerators, dishwashers, and washing machines. There is also an upper tier to Energy Star called the Energy Star Most Efficient. They publish lists of the most efficient appliances each year on their website, energystar.gov. And choosing appliances from one of these lists will lower the plug loads of the house even more. Lighting has made rapid advances in the past decade as well. Ultra energy efficient LED lighting is affordable and very cost effective. For the best quality light, you want to learn a bit about the bulb's specifications in order to choose the right one for the space you are lighting. First off, we need to learn about lumens to know how bright the bulb is going to be. From our past experience with traditional incandescent bulbs, we all know how bright bulbs were based upon the wattage. But you can't rely on wattage to tell you the brightness with LEDs. You need to learn about lumens. Here's a table with equivalent lumens for the 60, 75, and 100 watt traditional bulbs. So if you want task lighting in a kitchen, then choose a 1600 lumen bulb. But for low light areas, you want to choose an 800 lumen bulb. Then there's a specification for color temperature. And color temperature is really important to how we perceive light. When you want a warm, cozy light similar to the traditional incandescent bulbs, you want to choose a bulb with a color temperature of around 2700 K, which stands for Kelvin. This is similar light to early morning and evening light. For task lighting areas, you want to choose a bulb with a color temperature around 5000 Kelvin. This gives bright light similar to midday light. Then there's the color rendering index specification. This tells you how accurate the bulb's light will be to show a true representation of color as it would appear in natural light. The CRI is based upon a 1 through 100 scale, so any bulb with a CRI of 90 or higher will be good where accurate color is important. Just like with our food labels, you can now find lighting facts printed on light bulb packages to help you make the right choice. The lighting facts label includes brightness, estimated annual operating cost, lighting appearance that shows the Kelvin color temperature, and energy used. Sometimes it will also list the color rendering index. To take appliances to the better level, we look at upgrading the clothes dryer. Heat pump dryers are a relatively new option available that can have a big impact. Traditional dryers use a lot of energy to heat the air that dries the clothes. Heat pump dryers remove moisture by pulling water out of the airstream, using the refrigeration cycle that needs only a fraction of the energy. So these are a great choice to reduce the plug load and overall energy needs of the home. Another high-tech option to reduce energy use is at the stove, and this is an upgrade opportunity at the best level after you take care of the good and better opportunities. Induction cooktops use a magnetic field to vibrate the metal molecules in the pot and generate heat to cook. Heat is not actually generated in the stovetop at all. This is another great way to lower the operational energy loads of the house. And people who cook with induction cooktops give them high reviews. They're very fast and very responsive to adjustment. Many report that induction cooktops respond just as quickly as cooking with gas or propane. Number 9, mechanical systems. So at the good level, we're looking at a high-efficiency ducted heat pump or a condensing gas furnace. At the better level, ductless heat pump or inverter-driven heat pump or a highest efficiency condensing gas furnace. And then at the best level, add to the better or good a heat pump water heater or a condensing tankless gas water heater. So high-efficiency heat pumps use the ambient outdoor air as the heat source in the winter or as the heat sink to discharge heat in the summer. To choose a high-efficiency ducted heat pump, you look at the SEER and HSPF ratings. The SEER describes the cooling efficiency, but in our heating-dominated climate, you want to know the HSPF or heating efficiency. So look for heat pumps with an HSPF of 9 up to 13.5 for the high-efficiency good level. Heat pumps work just like your refrigerator or air conditioner, only in reverse. They move heat from air outside to the air inside the house. This does not follow the basic principle of warm moves to cold. The refrigerant cycle is able to do this magic by taking advantage of a scientific phenomenon known as latent heat. Latent heat is either absorbed or released when a molecule changes phase, and that's from a liquid to a gas, a liquid to a solid, or a gas to a liquid. The amount of latent heat is different for different molecules. So the latent heat of evaporation allows us to go upstream with heat energy against the natural flow of heat moving to cold. We can transfer heat into or out of a building with such high efficiency because we simply use the energy needed to compress the vapor and evaporate the liquid of the refrigerants. So energy is not being directly used for heat like it is with an electric resistance heater. The heat pump uses a small amount of energy to drive the motors to move 2.5 to 3 times more energy from one place to another. That means for every dollar going into the system in electricity, you get $2.50 to $3 of heat back out of the system. To ensure the heat pump is installed correctly, it should be commissioned so that it will run at these high rates of energy efficiency. Heat pump commissioning checks the refrigerant charge levels and adjusts it if necessary. Commissioning also tests the amount of air flowing through the air handler to make sure it meets the manufacturer's specifications. If the airflow is below the spec, the efficiency will be lower and it could shorten the life of the equipment. Commissioning also often includes installing or programming an outdoor thermostat that controls when the backup heat can be turned on. Without this outdoor control, the backup electric furnace heat may come on too often and use excessive amounts of energy. For gas or propane heating, at the good level, look for condensing gas furnaces as your go-to choice with AFUE efficiency ratings of 90 to 93%. To take the HVAC to the better level, you can choose a gas furnace with an efficiency rating from 94 all the way up to 99%. Also, don't forget to design and build so that the ducts and the air handler are located inside. For the electric heat pump option at the better level, consider using ductless heat pumps. These have very high efficiency ratings for a couple of reasons. First, no ducts ensure that the conditioned air is delivered only to the indoor space. The other contributor to their high HSPF and SEER efficiency ratings is the fact that these units have variable speed compressors and fans. This is known in the industry as inverter-driven heat pumps. This variable speed equipment can run on high to quickly bring the space up to the thermostat set point, but then it can ramp down and trickle heating or cooling to keep that temperature stable all day long. Of course, once it ramps down, it also uses very little energy to maintain even comfort levels for the homeowner. Ductless heat pumps offer many different options for the indoor unit: wall-mounted, ceiling recessed, or hidden in a soffit with short duct runs. They may be configured as a single-zone unit for open floor plan smaller homes, or multi-zone systems for medium to larger homes. Inverter-driven heat pump technology is now also being made for fully ducted systems. These traditional type air handlers use the same technology as the ductless heat pumps with a variable speed compressor to achieve very high efficiency levels of HSPF 10 up to 14. So if you prefer to stay with the traditional fully ducted heating and cooling, you can still take advantage of this high-tech equipment. But again, don't forget to include the ducts inside. Notching up our mechanical systems to the best category, we upgrade the hot water heater in addition to upgrading the HVAC. Heat pump water heaters are another relatively new mechanical system that represents a big leap in energy efficiency from the standard electric tank. And just like with the HVAC, for every dollar spent to operate the water heater, you get $3 to $3.50 of hot water back out of it. It takes the heat from the air in the space it's located in and moves it into the water stored in the insulated tank. It works best to install these in buffered, unconditioned spaces like garages or unfinished basements. For a high-efficiency water heating option with gas or propane, you can consider a condensing, on-demand water heater. These water heaters only heat the water when the faucets are turned on and can achieve up to 97% UEF efficiency ratings. We also have an Innovate category included in this section. Carbon dioxide heat pump water heaters are starting to show up in some Northwest projects. They have very high efficiency ratings, and instead of having the heat pump take the heat from the space around where it's located, it has an outdoor unit that pulls the heat from the outside air. The other significant difference is that they use carbon dioxide for the refrigerant instead of R410A. This is a great upgrade to help reduce greenhouse gas emissions, because when traditional refrigerants leak from heat pumps or air conditioning systems, the gases have a very high global warming potential. But if carbon dioxide leaks out of one of these systems, it has very little effect on global warming in comparison. And finally, number 10, solar electric. At the good level, build the home solar and electric vehicle ready. At the better level, zero energy or zero energy ready. And at the best, build to positive energy for electric vehicles. There are a number of considerations to think about when adding solar PV to a project. Of course, cost. How much solar can you add without breaking your budget? Then roof area can limit the size of the system. Shading from surrounding features may affect how much solar you can install for reasonable performance of the system. And then output of the system. How much power are you aiming for? A partial offset of the home's power needs, or is the goal to be zero energy? Then there's the question of grid or no grid tie-in. Most systems installed today are tied to the electric grid so that the excess power produced can be sold back to the power company with net metering. Then when renewable power is unavailable at night, the utility power supplies the house. The power grid essentially acts like a battery. But lithium-ion backup batteries hooked into the solar PV systems are starting to become more popular. The cost of the backup batteries is dropping because of the technology advances and economies of scale. Adding a backup battery and backup inverter allows a home to weather the storms, with critical needs powered up. The rolling blackouts that are happening in California on a regular basis to prevent forest fires are also increasing consumer demand for solar with backup capability and will likely reinforce this trend. Throughout the Northwest, There's plenty of solar resource, which is the average power hitting the Earth each day, to make PV a viable investment. Here are the numbers that show the solar resources of various cities throughout Oregon. The solar resources of these Oregon cities are not that far behind Miami, with its abundant sunshine and very southern location. Then looking at Germany, which has the most solar power installed of any nation, the average solar resource is only 3 kilowatt hours per meter squared per day. And we see that there is more solar power striking the ground in every Oregon city to make PV viable. And here's the numbers that show the solar resources of various cities throughout Washington. Again, plenty of power to capture throughout the state. Adding solar systems is a great investment and adds significant value to the home. A study done by the U.S. Department of Energy's Lawrence Berkeley National Lab looked at the sales of homes with solar across the U.S. and found on average that the PV system added $4,000 per kilowatt of PV installed at the time of sale. The typical residential system size across the U.S. was a 3 kilowatt system, and the average sales premium was $12,700. The average premium was even higher in California, where the solar market has a longer history, with homes earning around $15,000 premium at time of sale compared to similar homes without solar. And then, of course, the solar system also provides an immediate return on the investment by producing power and lowering or eliminating utility costs as a direct and immediate benefit to the homeowner. Here's a couple of publications you can tap into for more information on solar systems. A Homebuilder's Guide to Going Solar, produced by the U.S. Department of Energy, and the Oregon Solar Electric Guide from Oregon Department of Energy. We'll include the links to these documents in our resources list. So let's have a look at the good, better, and best. At the good level, you build your projects to be solar and electric vehicle ready. This means you design and build the homes so that these systems can be installed in the future at a lower cost and without barriers to producing power on site. That means optimizing building orientation, keeping the sun-exposed roof areas clear of obstructions to adding solar panels by avoiding chimneys, vent pipes, and so forth, ensuring that the electric breaker panel has the capacity and circuits available for a solar system. You provide clear wall space to install the inverter and other electrical components. And then you either pre-wire or add a conduit from near the breaker panel to up below the roof deck for easy installation of the wires in the future. Another thing that will affect the available roof space for solar are fire regulations. There are setbacks required for the firefighters to be able to have access to the roof. You want to find out what these setbacks are in your local jurisdiction in order to accurately calculate how much usable roof space will be available. In most solar-ready projects, builders will have the electrician install a conduit for wires to be pulled in the future up to the underside of the roof, ending in a junction box. That conduit runs down to another box near the breaker panel where the inverter is to be installed. The breaker panel also needs to have an empty 240-volt breaker space reserved and labeled for future solar system tie-in. To build electrical vehicle ready, it again is simply having a reserved and labeled 240 breaker space in the panel so a fast vehicle charger can be added. EV purchases are predicted to grow quickly in the near future, so this is definitely a feature to start adding to your projects to align with this demand. To take solar to the better level, you simply install the solar panels to bring the high-performance, PV-ready home to the point where the system produces as much energy on the roof as is needed to operate the house below the roof. And then you've built a zero-energy home. But if that's outside the budget, you aim for zero-energy ready by building a high-performance home with solar ready. Zero-energy projects have been quickly adopted in the marketplace by high-performance builders over the past 5 to 10 years. The early adopters were the bigger budget custom homes. The second wave happened in affordable and multifamily projects. And lastly, now there are spec and production builders who have started building zero-energy homes. The word is out there on zero-energy homes, and it's spreading. The homeowners who live in zero-energy homes are so happy with the quality of living in them and the really low operating costs that some of them are starting to shout from their rooftops how great these homes are and influencing future home buyers. But how do you make this pencil out? There's clearly a price premium for adding all this energy efficiency and solar power to your project. Well, you need to help home buyers connect the dots between their home mortgage and their power bill savings. If they take the savings from utility bills and apply that to their monthly mortgage payment, zero-energy homes can be as affordable as traditionally built homes. Let's look at some numbers to see how this could work. A $10 per month in energy savings can buy $2,000 more house, or at least $2,000 more mortgage. So owners can easily save $100 per month on energy costs, which would allow $20,000 higher mortgage, with no impact to the owner's monthly budget. Or another way to cover the premium is with size reduction, which can free up additional funds. If construction costs are at $200 a square foot, then reducing the overall size of the home from 2,400 square feet to 2,000 square feet could yield up to $80,000 to be put towards energy efficiency upgrades and a solar system. Rocky Mountain Institute released a study on the cost premium and a homeowner's willingness to pay for zero-energy homes. They did research in 4 metropolitan markets across the country, in Houston, Atlanta, Baltimore, and Chicago. They found the additional incremental cost to make a home high-performance, zero-energy ready to be around 1 to 2.5% above a code-built home. The cost premium to take a home all the way to zero energy by adding the solar came out around 6.5 to 8%, depending on the market. So, of course, this is a significant cost for the upgrades, but we can see that zero energy is no longer limited to only high-end custom home budgets. They also surveyed home buyers in each of these markets to see what they were willing to pay. On average, the current home buyer was willing to pay 4% more for a high-performance home. So that easily covers the cost premium for the zero energy ready, super energy efficient home. But as we see in this chart, the 4% willingness to pay did not quite cover the added cost for the solar system to take the project to a zero energy level. But as the cost of solar systems continue to drop ever lower over time, and as consumer awareness grows about how great living in zero energy homes is, this gap will shrink and zero energy homes will become a mainstream expectation. Another factor that will lead to widespread adoption of zero energy is that the cost premium will go down. This same Rocky Mountain Institute study projected that by the year 2030, the added costs of zero energy homes above code level will be nearly half of what it was in 2018 at the time of the study. The cost of the materials will continue to drop as more builders embrace high-performance building, and the energy codes will evolve and continue to require higher performance, narrowing this gap. After looking at these numbers, the writing's on the wall. The earlier you can embrace high performance and zero energy, the better position your business will be in to capture this future market demand for zero energy homes. So how do you go about planning, designing, and building a zero energy home? Well, these 5 steps to zero energy are one good approach. Design with an efficient use of space, build a high-performance shell, right size, and reduce the energy demands from the mechanical systems. Add very efficient appliances and lighting to lower operational plug loads, and then add renewable power to meet the needs of the home. Sound familiar? If you build to the best categories of what we just covered in this course, you're pretty much there. So, in more detail, step 1, the efficient use of space. Size matters a lot in energy use, so try to avoid square footage bloat. Surface area to volume ratio should also be as low as possible. A 2-story home versus a 1-story for the same square footage will lower this ratio. Orientation matters for both energy use and energy production. And designing for passive cooling can also help lower air conditioning loads. Step 2, build a high-performance shell. We need to control bulk water, airflow, heat flow, and vapor drive. Want an integrated air barrier design. Want to build the highest R values and use the lowest U values in windows wherever possible. We want to tune the SHGC of the windows to orientation, and we want to avoid thermal bridging through the structure. Step 3, right-sized mechanical systems. We want to make sure software is determining the size of the systems, not square footage, by working with HVAC contractors who use design software and not rule of thumb to size their systems. You want to work closely with the HVAC contractor on design inputs specific to the project that you're building. Heat recovery ventilation is a must. Distribution location can make or break efficiency ratings, so we want to carefully consider distribution design on the space heating and the water heating systems to maximize energy efficiency. Step 4, high efficiency lighting and appliances, includes LED lighting everywhere and only Energy Star appliances installed in the home. And then step 5, add the renewable power system, sized to meet the power needs of the home as estimated with energy simulation software. On the left is the traditional 5-step approach to zero energy that we just covered. It was the most cost-effective strategy originally because the cost of solar was so high a few years ago, and you wanted to minimize that expense. But as the price of solar systems has dropped so dramatically in recent years, some builders have flipped the 5-step approach. They start with evaluating how much solar the roof space and project budget will accommodate to calculate the power that can be produced. Then they work with the energy model to dial in the mechanicals, square footage, building shell characteristics, and lights and appliances to figure out the energy needs and match the power to the solar PV. Either approach can work as long as you have the benefit of an energy model to help you size all these parts together in order to balance everything. To keep zero energy within reach for the average buyer, one Portland area builder likes to say he aims to build a kite, not a rocket ship. Both will get you off the ground, but a lot more people can buy the kite. And as we've seen in this course, there are many paths to building high-performance buildings. So as with all parts of the project, careful planning, material selection, and design can help keep your costs under control. A cost-effective path to zero energy ready is to start with a green home certification that includes a verifier who can help you with energy modeling, consulting, and verification throughout the build to nail your high-performance goals and keep your costs under control. You want to integrate advanced features into your projects like ducts inside or ductless heating and cooling, include solar-ready features, and upgrade the entire shell to minimize heating and cooling loads. Maximize the roof design, keeping it free of obstructions, for adding the solar system in the future. Taking number 10 to the best level, it is feasible to build a positive energy home. If the roof space allows, you install more capacity so that it produces more power than the home uses, so it can be used to charge an electric vehicle. This makes an even bigger impact because now the homeowner can live and drive with the renewable power of the sun. And as we discussed earlier, storage batteries will become more affordable in the not too distant future, so the excess energy can be stored for later use. We're at a very exciting time in home building. Many forces are coming together to create a positive change for how we produce and use energy. These welcome changes will not only benefit us personally with very low energy costs, they're going to benefit humanity and the planet by helping us tackle the challenges of global climate change. Local programs and incentives. Please visit the Better Built Northwest website at BetterBuiltNW.com to find the energy efficiency programs that are offered in your area. Once on the website, click on Programs, and then click on New Construction Utility Programs, where you can find energy efficiency programs offered by Northwest utility companies. They'll offer cash incentives to help offset the cost of energy upgrades. Backing up and clicking on Home Certification Programs brings up a list of regional and national green and energy efficient home certification programs offered. It's through these utility-based or home certification programs that you'll be able to locate local third-party verifiers to help you with your projects. Many of the utility-based energy efficiency programs participate in the Better Built Northwest Single-Family Performance Path. This awards incentives to single-family projects based upon the energy savings calculated with energy modeling. The Performance Path Incentive Estimator tool is available to verifiers participating in the program who can use it to estimate savings, percent improvement over code, and builder incentives for homes seeking qualification in a utilities performance path program. This can be really helpful to you as you plan out your upgrades and budget. Another great way to find a verifier in your area is to click on Find a Professional on the Better Built Northwest website. Once the tool opens, then just click on Rater Verifier and it will filter the results and show you the verifiers in and around your zip code. Our final segment of this course covers process improvement. Change can be challenging, but using systems to guide that change can help smooth the transition. Traditionally in manufacturing, quality control happens after the product is made. But with home building, this is the most expensive time to make corrections, so you want to implement quality assurance throughout the build. So when does it happen, and who's going to do it? Of course, prevention is better and less expensive than detection. For effective quality management, it's key to plan for a system in advance. Identify responsible parties throughout the building process. Verify proper installation at each stage. And documentation is a great way to ensure success. The focus of the quality assurance for high-performance shell is primarily on the installation of the insulation, air sealing, and the durability details. One type of documentation that works well for QA are checklists. An Energy Star New Homes program has developed a series of checklists for air sealing, ductwork, framing, and insulation that you can use or adapt to your own workflow. They're available for free as a download on the Energy Star website. An effective strategy is to implement a quality construction chain by including key requirements in your work scopes for each trade that works on the shell. You want to describe how each person must check upstream work before beginning, how each person must know how to do their work, how each person must know all the critical details are done defect-free, and they must check their own critical work details at completion. And you can find all of these critical work details listed in the Energy Star checklist documents. And once again, participating in a certification program that includes a verifier is a great way to add another set of eyes to help you with your quality assurance plan. They will verify all of these details to help you meet your high-performance goals and provide the highest quality home to your customers. We hope you enjoyed this course and found it helpful for taking your projects to the next level of high performance. Thank you very much for your time.